All right, so with 7.2, we're moving from, well, really the application of just accumulating things to actually finding areas in the plane. Not just the area between the curve and the x-axis, which, by the way, we've already found, or at least approximated using RRAM, LRAM, and MRAM. But we're actually going to find the exact area. Let's go ahead and get started with this. All right, so we've got these two curves. Y1 equals 2 minus x squared, and y2 equals negative x. That's this line right here, and there's the parabola right there opening down. How can we find the area between these two curves? Well, we could split the area up into several sections and use subtraction and figure it out, but there is an easier way. Think about a very thin vertical strip. Now, guys, while we're thinking about this, I want you to also think about the fact that this vertical strip is also nothing more than just a rectangle with a very, very small width. We talked about this before. If we let the dx, the width of that strip, go to nothing, then we're going to have an infinite number of strips down through here, and we're going to get a very, very accurate, if not exact, answer to our problem. And that's what we're going to do here. So if we think about this thin vertical strip, it has a thickness that is dx. And what is its length? Well, its length is whatever this y value is right here minus whatever this y value is right here. So it's essentially y1 minus y2, or 2 minus x squared minus negative x. So if that's the length of the strip, and we know the width is dx, we can find the area of this rectangle by the y2 minus y1 height times the width. And when we multiply those together, length times width gives us 2 minus x squared plus x minus a negative, made this a plus, times dx, which is the width. And that's the area of this one little strip here. Well, how do we add all the strips starting from over here all the way to over there? Well, that's where integration comes in. If we add all the strips, we're going to get the integral from -1, that's this intersection over here, to 2, that's where they intersect over here, of 2 minus x squared minus x dx. So that's where we found this intersection over here. This is at -1, and this intersection over here is at +2. That's where the two things intersected. So we can find this by integrating. If we integrate the 2, we're going to get 2x. If we integrate the negative x squared, we're going to get -1/3 x cubed. If we integrate the x, we're going to get 1/2 x squared. Then evaluate it from -1 to 2 by plugging and chugging. Plug in your upper bound, and then subtract when you plug in your lower bound. So plugging in the 2, we're going to get 4 minus 8/3 plus 4 halves, which is 2. Minus, plugging in the -1, we're going to have -2 plus 1/3 plus 1/2. Where we square the -1, it ends up making this a +1. When we cube the -1, gives us a -1 times this one makes that a plus. So then when we simplify all that down, we get 9/2. So the area enclosed by these two blue figures, the blue function there and the blue function there, is 9/2 of whatever units we're using here. So the formula for the area between the curves is the area equals the integral from a to b of f1 of x minus f2 of x, where f1 of x is the upper and f2 of x is the lower. So this is the upper function, and this is the lower function. Now, if you're looking at a function where those two positions actually change, the upper and the lower swap places, they intersect and change, then you have to split it up into multiple integrals. Now, we're going to use this so much, I don't want you to memorize the formula. I just want you to know how to set it up to do it. Because this formula right here means nothing if you don't know that f1 of x is the upper one and f2 of x is the lower one, and that a to b is where we're integrating. So I would much rather you learn to apply and analyze how we're going to find it as opposed to memorizing some formula. All right, so we're not always going to be able to draw that line vertically. In this case, if we draw our line vertically, notice here we're okay. We're just going to integrate this thing right here because we're going down to 0. But what happens when we get over here? Well, right there at that point, well, roughly about that point right there, it transitions, and then we actually have to do the difference. So you'd end up setting up two integrals here. One integral from here to there, and the other integral from there to the intersection point. Well, that's more work than we really want. And that would be the integral that you'd have to set up. And then you would have to solve those. Well, if we can find the same area using a horizontal strip. And notice in this case, the thickness of this is vertical, so it's going to be dy. Now, if you do that, that means your y value is what you're integrating with respect to. So you're going to start at 0 and go all the way up to this intersection point, but we're going to notice that in the y value, not the x value. Well, in the same way, we have to solve these equations right here so that they're in terms of y. So we have to find the length of the strip by solving for x in terms of y. That will let us express the length of this thing, the horizontal length, by the way, not vertical, the horizontal length of this thing in terms of y. So if we take y equals the square root of x and we convert that over, we're going to end up squaring both sides, and we're going to end up with y squared equals x, or x equals y squared. If we take the other one, y equals x minus 2, we want to solve for x. We're just going to add 2 to both sides. So now, which one is the, quote, upper and which one is the lower? Well, in this case, since we're going horizontally, we're not really looking for technically upper and lower, except for we're looking for upper and lower in terms of x. Which one of these functions at any given horizontal line has the greatest x value? Where it's going to be this one. So that's the one we're going to start off with. And you're going to subtract the one that's going to have the smallest x value for that given horizontal line. So we're going to subtract this equation over here. So you would do y plus 2 minus y squared. You would not do, like you would here, the square root of x minus x minus 2 in parentheses. You would do y plus 2 minus y squared. And the reason why is because we want to find what the length of this is in a positive way. Well, we're measuring this in x values. So this x value right here is greater than this x value right here. So when we take this value, which is that x value right there, and we subtract this part right here, well, what's left? It's just going to be this part in here that we actually want the value for. All right, so once again, all we're setting up is the length of the strip times the width of the strip. That gives us the area of this one green strip right here. And then once we find the area of that thing, we can integrate to add up all the areas we're going to find. Now, where are we going to go from and to? Well, we already talked about the fact we're starting at 0. How would we find where we intersect up here? Well, the way you find where they intersect, we're looking for a y value. So we want to actually solve this thing by setting them equal to each other. So if we set these two things right here equal to each other, we're going to be able to find out what y value is at this point right here. So let's go ahead and put these together. They're both equal to x, so we know they should be equal at that point. So y squared equals y plus 2. We're going to move the y plus 2 over, and we're going to get y squared minus y minus 2 equals 0. Factor that, and we're looking at y and y. Different signs, 1 plus, 1 minus. The largest number is going with a minus. So what functions, what values are we going to have? We're going to have numbers that multiply to give me 2 and subtract to give me 1. That would be 1 and 2. And the 2 goes here, and the 1 goes there. Now when we solve this, we're going to get y is equal to -1 and positive 2. We set each one of these equal to 0 and solve. That's what the y values are. Now, this one is going to be the point 4, 2. Now, where does this other one come in? Well, think about this. If you had this line right here continue on, we had this parabola, side opening parabola continue on, we would have an intersection down here. So that's where that other value comes in, but we're only looking for the 2. So we're going to integrate from 0 to 2. And evaluate. That's why we're integrating from 0 to 2. Sorry, I didn't even think about the fact that we already had the 0 to 2 there. I just want you to know how to find it. So then we integrate each one of these terms individually and plug and chug again. We're going to have 2 plus 4 minus 8/3. Now there's only one set here because what happens when you plug in 0? Well, all these are going to be 0. So you can think ahead and notice that that's going to happen. So then, when we simplify that, we get 10/3. So the area enclosed in this figure between this function, and the y and the x-axis, it has a value of 10/3. Square units of whatever. All right, so the general strategy for the area, to find the area between curves, is you want to first sketch the curves. If you do not already have a sketch provided to you, you want to sketch the curves. Most of the problems that they're going to have, that you're not going to have a graphing calculator for, you're going to be able to sketch them rather easily. They're going to be square roots of x. They're going to be x squared plus 1, which is nothing more than a parabola shifted up 1 unit. Basic graphs like that you should know if you remember the base graphs from pre-cal. If you do not, you need to go back and look at those graphs because, well, they're important. All right, the second thing, you need to decide whether you're going to use vertical or horizontal strips. Whichever is easiest is the one you want to pick. To write the formulas for the length of the strip and or which will let you integrate fewer times. Now, the reason it says the length of the right formulas for the strip, you got to remember some are going to be very, very difficult to solve for x. For instance, if you got x equals y squared plus y, something like that's not going to be easy to solve for y. So leaving it in terms of x is a lot better. Part 3, write an expression for the area of the single strip. Draw the strip on your curves and identify if the width is dx or if the width is dy. You've already decided which one. And then write an expression for the area of the strip in terms of whichever x or y you've got the d for. If you have dx, the length must be in terms of x. If you have dy, it must be in terms of y. So otherwise, you're going to have some expression like this. You're going to have an integral from 0 to 1 of x squared plus 3x minus x, and you're going to have a dy out here, and well, integration like that, that's Cal 3 stuff. We're not dealing with that, so you should not have to deal with that, and that would not find the area under the curve anyway. That would actually find something, how this thing's behaving in the y direction. That's what that would find. So you don't want to deal with that. All right, and then the fourth thing, find the limits of integration. If using dx, the limits are x values. If using dy, the limits are y values. So way up here when you decide on your vertical or horizontal strips, remember that is defining everything. That's why it's so important for you to do that part first. You want to identify that so that you can identify whether you need to find all this stuff in terms of x or in terms of y. All right, and then the very last thing, integrate. And the value that you come up with will find the area. All right, and that is all there is to finding the area between two curves. Now, here is another way to look at it, remembering that the integral of a sum or difference is equal to the sum or difference of the integrals of each function. You can split it up into parts. If you're doing the integral of f of x minus g of x, you can split that up into the integral from a to b of f of x dx minus the integral from a to b of g of x dx. You're essentially doing that anyway when you do it term by term, but I just wanted to clarify again that what you're finding is just the integral of each individual term. Also, here's the neat thing, is that you can actually see with this that if you find the area under f of x and then subtract the area under g of x, you're finding the area between the curve. So this part right here would find the area between f of x and the x-axis. This one would find the area between g of x and the x-axis. So if we have, let me draw something here, or try to anyway. We have, this is f of x, and let's say this is g of x, and we find the area under the curve with this one, which is all this, and then we find the area under the curve for your green, for your g of x, and that's this part right here. Well, if you take that area that I just colored green away from it, what do you end up with? Only the area between the two. So that's what you're seeing here. All right, that's it.